In this lesson, we will explore the defining characteristics of periodic and sinusoidal functions and how to describe them using graphs, equations, and real-world situations. So before we start, we want to explore what is a periodic function. So by definition, a periodic function is a function whose graph repeats at regular intervals. So the graph provided is an example of a periodic function. The y values in the table of values of periodic function shows a repetitive pattern when the x values change by the same increment. So if you notice on the graph, one cycle, which is in red, then it repeats itself again, is in black, then it repeats itself again, and it's in red. So it continues, continues, continues. So the cycle would be the smallest complete repetitive pattern of the graph, and the period is the length of one cycle, that change in the independent variable. So meaning when the cycle begins, you look at that x value. When the cycle ends, you look at that x value, you take the difference, and that would represent that period. Now, looking at the peak is always the maximum point on a graph where the function changes from increasing to decreasing. So in our example here, our maximum looks to be at 2. So that's your maximum. So that would be your peak. The trough would be your minimum, which happens to be a -1. So that would be your trough. And that's your minimum. So again, the peak is the maximum point on the graph where function changes from increasing to decreasing. The trough would be that minimum point on a graph where the function changes from decreasing to increasing. Amplitude. Amplitude is that vertical distance from the axis of the curve to the maximum or minimum value. The amplitude can be found using the following equation. So the maximum value minus the minimum value divided by 2. So when they say the axis of the curve, well, the equation of the axis is the horizontal line halfway between the maximum and minimum. So we have our periodic function. We look at the one cycle, you look at the max and you look at the min. The halfway horizontal line that halfway between the maximum and minimum is considered that equation of axes. The equation of the axes can be found using the following equation. You would take the maximum value added to the minimum value and divide it by 2. So see how that difference from the amplitude. You would take the max minus the min divided by 2 for the amplitude, but in the equation of axes, the halfway horizontal line halfway through is the equation of axes. So given the following periodic function, we can tell, reading off the graph, that the maximum value, our peak, is 5. Our lowest, this is our trough, our min, which is equal to 1. Okay, so this is considered a peak, our max. That would be our trough. The period is when one full cycle occurs. So you can tell the easiest way to determine what the period would be is from max to max and min to min. So if we look here, you would have to compare it to, again, that independent value, so the x value when it starts, when it finishes. So 3 and 11. So the period would be the difference between that. So it'd be 11 minus 3. So it means one full cycle occurs within 8 units. Okay. Now, the equation of axes is a halfway point. So let's use the information we have above. Use those equations to help us out. We know the max is 5, the min is 1. So if we wanted the amplitude, which we could read right off the graph, which would be right here, the distance from the halfway mark to the peak, that shows to be an amplitude of 1, 2. The equation of axes is right, that dotted line, which is y is equal to 3. So let's verify that using the equations. So the amplitude is the max minus the min, divide that by 2. So A is equal to 5 minus 1, which is 4, divided by 2, which is 2. The amplitude is always an absolute value, so it's always positive. Okay, it does the equation of axes work out as well? Let's see that. So 5 plus 1, divide that by 2, y is equal to 6 divided by 2, which is equal to 3. So it's always that horizontal line, so it's always that equation y equals. Okay, looking on to example 1, we want to determine which of the following graphs of functions are periodic. Justify your decision. So if you look at the first graph, again, periodic function means that the function repeats at regular intervals. So that means that it would reach that max and min over time, okay, continuously. If you look at example A, that doesn't happen. So we know that that is not a periodic function. Looking at B, notice that it is the same pattern that continues. So we're going to say that definitely is periodic. So the graph is periodic since it repeats at regular intervals. Okay, so we can see that the period, so one cycle would be, that's one cycle, is 4. From 0 to 4 is when one full cycle, and then it keeps repeating, and it keeps repeating. Looking at C, again, we see a pattern there. It keeps repeating itself. That would be one cycle, then it continues, and then it repeats again. So on this particular graph, we have 3 different cycles. So again, the cycle, when one full repetitive pattern occurs, the period is that length of time it takes for that cycle to occur. So in this case, we're going to say the graph is periodic since it repeats at regular intervals. Okay, looking at D, no, it doesn't repeat. It just keeps increasing. So we know that that is not periodic. Okay, looking at number 2, it says determine the period, amplitude, and the equation of the axes for the following functions. Now, again, we said the period is when one full cycle occurs. It's always best to start from max to max or min to min. That is when it's easier to calculate. You're looking at those x values when it starts the cycle and when it ends, and that difference represents the time it takes for one cycle to occur. So in our case, we have the following graph, and we first want to identify the max and the min. So we're going to say the peak, the max is 4, and here the min looks to be -1. -1. Okay, when does one full cycle occur? So I suggest, and I'm going to use a different color just to help us out. We're going to say it starts, say here, and then it comes back to that point here. Okay, so let's see at what independent variable value does that occur. So it looks like, and always keep in mind your scale. So in this case, it looks like our scale is going up by 2s. So I'm going to remind myself of that. So I'm going to put a 2 in there. And then this would be 6. And it looks like it gets back to that max at 7. Okay, so when we're trying to figure out the period, we want to identify when does one full cycle occur, when the cycle starts. Let's figure out that x value where it starts and where it finishes. The difference would be that period. So the period is equal to 7 minus 2. So the period in this case is equal to 5. The amplitude, we know it's always equal to max minus the min, divide that by 2. Max is 4 minus the min, which is, oh, I put -1, but we know that's -2. Keeping the scale in mind, I apologize. Always keeping the scale. I look, maybe boo-boo. It's easy to make that mistake. The scale is 2 as well. So in order to avoid that, maybe perhaps put in those values so you don't overlook it. Okay, so I just assume down by 1 is -2, -1, but the scale goes down by -2. So keep that in mind. So we have minus -2 divide that by 2. 4 plus 2, which is 6. 6 divided by 2, which is 3. So the amplitude is 3. The equation of axes, so this was the amplitude. Equation of axes. Y is equal to max plus my min, and divide that by 2. So y is max, 4 plus -2, divide that by 2. We know 4 plus -2, which is 2. 2 divided by 2 would equal to 1. And we can observe that all on the graph. So I'm going to again use a different color, dotted line. And y is equal to 1 is definitely that equation of mass, that halfway mark. And that would be my amplitude. A is equal to 3, the distance from the equation of axis to the highest point. And if you see the other way, again, that is also equal to 3. So it's difference from the equation of x to the max, from the equation of x to the max and to the min. Okay, so looking at B, we have, and same idea, start with the period. Always best to go from max to max. Okay, and which independent values that happens. So we're going to say, okay, keeping in mind the scale. Okay, so the max, that's when one full cycle occurs. Cycle. So then the period is going to equal to 2 minus 0. So the period is equal to 2. Okay, the maximum we see is 1. So max is equal to 1. Min is equal to -1. So the amplitude is going to be max minus my min. We're going to divide that by 2. Max is 1 minus -1. Divide that by 2. So the amplitude is 1. The equation of axes is max plus min divided by 2, which is equal to 1 plus -1. Divide that by 2. Y is equal to 0. Okay, looking at example 3, we have the graph shows Brandon's height above the ground as a function of time as he rides a Ferris wheel. Now notice he gets on to, or the minimum point, so min is equal to 1, and then the max is equal to 7. Okay, so state the maximum height of the ride. So we can say maximum is equal to 7, minimum is equal to 1. And of course, we're given units, so that's meters. So the height is in meters, the time is in seconds. How long does the Ferris wheel take to make one complete revolution? Well, that would be your period. Okay, so that would be your period. So if we look up at the graph, okay, so we can, at this point, because it's starting at its minimum, we can take from minimum to minimum. So there we go. So one full cycle is one cycle. So when does one full cycle occur? The period would be the difference in those x values. So period was equal to 8 minus 0. And the units are 8 seconds. So that means the ride on the Ferris wheel takes 8 seconds to do one full cycle. So it says, how long does it take? So therefore we can say it takes, always answer the question with word problems, takes the Ferris wheel 8 seconds to make one complete revolution. Okay, C, what is the amplitude of the curve? How does this relate to the Ferris wheel? So the amplitude we know is max minus the min, divide that by 2. So we know the amplitude is going to equal to 7 minus 1 divided by 2. 7 minus 1 we know is 6. 6 divided by 2, which is 3. So the amplitude, therefore, what is the amplitude? Therefore, the amplitude is 3 meters, and which represents, how does it relate to the Ferris wheel? Which represents the distance from the center of the Ferris wheel to the top or the bottom, the same distance. Okay. Determine the equation of the axis of the curve. Well, we know the equation of the axis is always, oops, y is equal to max plus your min. Divide that by 2. So the max we know is 7 plus my min, which is 1. Divide that by 2. 8. 7 plus 1 is 8. 8 divided by 2, which would equal to 4. Okay, what is the range of this function? So we know the lowest is always 1 meter. That's when you get onto the Ferris wheel. The highest you'll go is 7 meters. And then it just keeps going. So we know our max and min. So if we wanted to know the range of the function is, it can be any value. However, y is always going to be greater than 1, but less than or equal to 7. Okay, so just to know, y represents the height. Y equals the height, and x is equal to time. Okay, so looking at some properties of sinusoidal functions. A sinusoidal function is a periodic function whose graph looks like a smooth symmetrical waves where any portion of the wave can be horizontally translated onto another portion of the curve. So recall, periodic function. A function is periodic if it has a pattern of y values that repeat at regular intervals. A cycle is one complete pattern. The period of a function is the horizontal length of the cycle, and the amplitude of a period is 1/2 the difference between the max and the minimum values. So a sinusoidal function is a function that is used to model periodic data. So for example, the graph shows an individual's 3 biorhythms: physical, emotional, and intellectual for 36 days from 0 on to September 30th to November 5th. Right, so notice it keeps repeating itself. Graphing the primary trigonometric ratio sine, cos, and tan will reveal that they are also sinusoidal functions. So let's explore the graphs of the primary trigonometric functions. So again, sine theta, cosine theta, and tan theta. So part A, we're going to graph f of x is equal to sine of x on the following intervals between 0 and 360 degrees. So we're just going to put these angles into our calculators to figure out what is sine at 0 degrees, at 30, at 60, at 90, and so forth. So if we took sine of 0, it would be 0. Sine 30 would be 1/2. And we know this because these are special triangles. Sine of 60 is root 3 over 2. Now, because we're going to be graphing it, I'm going to just put an approximate 0.87. Sine of 90, we know is 1. Sine of 120 is root 3 over 2, which again is 0.87 about. Sine at 150 is 1/2 and 0. Sine at 210 is negative 1/2. Sine 240 is negative root 3 over 2. Sine at 270 is negative 1. I'm going to get root 3 over 2, negative 1/2, and then 0. Okay, so let's graph that. So at 0, we're at 0. And again, the scale on the x-axis does go up by 30s to make 150, 210, 240. The scale is very critical. We want to make sure, if you're not sure, write in all the numbers to avoid any silly mistakes. So we know at 0, we're at 0. At 30, we're at 1/2. So we're going to spread this out because we can. We're a scale. So I'm just going up by 0.25s and -1. So spread that out because you do have the room. We got to decide what the scale was. So therefore, I'd like to spread it out. So at 0, we're at 0. 30, we're at 0.5. At 60, we're at 0.87. At 90, we're at 1. And then we're at 0.7. Then we're at 0.5. At 150. At 180, we're at 0. Then we're at negative 0.5. Negative 8.7. Negative 1, negative 8.7, 0.5, and 0. So what you notice, we have a nice smooth curve like such. So this would be y is equal to, well, let's say f of x is equal to sine of x. Okay, when we will use the quadrantal angles for our key points. So what that means is when you're looking at the quadrants, so 0, 90, 180, 270, 360. So those are the key points. So just like we looked with the other functions, there's those parent key points. These 5 points are the key points for the sine function. So when you're looking at y equals sine theta, you're going to remember that the key points at 0 degrees, so think of your quadrants, 0, 90, 180, 270, 360. So at 0, we're at 0, then we're at 1, 0, negative 1, 0. We know it's a nice smooth curve, so these are our key points. We don't take a ruler and connect them. We know that it's in it. We just don't have to include those points in between when we're using a table of values because we will be transforming these functions. So we do need to have those parent function key points, and these would be our points. The quadrantal angles, so 0, 90, 180, 270, 360. Okay, so moving on, let's see what can we gather from this graph? So complete the following information of its characteristics where x is greater than or equal to 0 but less than or equal to 360. So what is the period? When does one full cycle occur? Well, that looks to be the full cycle occurs between 0 and 360. It goes up, it comes down, and then comes back to the equation of axes at 0. So we're going to say that would be 360. One full cycle occurs between 0 and 360. The amplitude, so that distance from the equation of axes, the halfway mark, which is y equals 0, that distance would be a is equal to 1. The maximum is equal to 1, the minimum. So the peak is 1, the trough is negative 1. Okay, so the amplitude was 1. The x-intercepts, where does the graph cross the x-axis? So we have them at 0, 180, and 360. Okay, so putting that on our graph, we have 0, 180, 360. So remember, it's for that one full cycle. So 0, 180 degrees, and 360. Okay, the domain. We know that it just keeps going. So really, there are no restrictions. We can say x is an element ring, other than, of course, they gave us that restriction. But that would just keep going. That would just keep going. The maximum value was 1. The minimum value was negative 1. Now, y values are important because there's a max and a min. So y is an element of real. However, y can be greater than or equal to negative 1, but less than or equal to 1. So the domain was x can be anything Range was restricted because there's a max and there's a min. So with the range, our maximum value is 1, our minimum is -1. So y can be anything, but it has to be greater than -1, but less than 1. Okay, let's see what cosine function would look like when we graph it. So again, we're going to use those values when we're just going to put into your calculators, or we're using our special triangles. So at 0, we're at 1. 30 is a special triangle. So for cos 30, we know it's root 3 over 2. So again, when we graph, it's about 0.87. Cos of 60 was 1/2. 90 is 0. -1/2, negative root 3 over 2. If you took cos 180, it'd be -1, negative root 3 over 2, -1/2, 0, 1/2, root 3 over 2, and then back to 1. Okay, so let's graph that. Again, we'll use the same scale. The x will go up by 0.25, so that's 0.5 of 1, negative 0.5, and -1. These are going up by 30s. Okay, so we're starting at 1. At 0, we're at 1. At 30, we're at 0.87. Then we're at 0.5. Then we're at 0. Then we're at negative 0.5. Just using the table of values to help me graph this. 0.5. And there we have it. And this f at x is equal to cos of x. Okay, so again, we're going to look, we're always using that quadrantal angles for key points. So 0, 90, 180, 270, 360. So at 0 or 1, 0, -1, 0, 1. So we're starting at the maximum. Maximum, we come down to 0, then back to -1, 0, back to 1. Okay, so let's complete the following information of its characteristics. Complete the following information of its characters where, again, x is greater than or equal to 0, but less than or equal to 360. So when does one full cycle occur? 360 degrees. The amplitude, again, the amplitude is that distance from the equation of axes, as we can see off the graph. That's your max. That's your min. Okay, so the amplitude would be that distance, which we know a is equal to 1. Okay, the x-intercepts. In this case, where does the graph cross the x-axis? At 90 degrees and at 270 degrees. The domain. Domain, again, unless given restrictions, that's one cycle. Otherwise, x is an element of real. The maximum value we saw was 1. The minimum was -1. The range would be, again, it can be any value, but it has to be, the y value has to be greater than -1, but less than or equal to +1. Okay, what you probably noticed is that the graphs of the f at x equals sine of x and f at x cos of x are similar in shape and have an amplitude of 1 and a period of 360. Next, we will explore the tangent function. So f at x is equal to tan of x. The tangent function is also periodic. However, its periodicity varies from the sine and the cosine function. Let's explore. So recall, tan of x is always sine of x over cos of x. So in part C, we're going to be graphing f at x is equal to tan of x on the same interval where x is greater than or equal to 0 degrees, but less than or equal to 360. So again, just one full circle. So looking at tan at 0 degrees, if we put that into our calculators, we would get 0. Tan of 30 is 1 over root 3, but we know rational end is the denominator, root 3 over 3, rounded to 2 decimal places would be, because hundredths means 2 numbers after the decimal. Tan of 60 is just square root of 3. Now, if we take tan of 90, you're going to see error on your calculator, which means there's something called it's undefined at this point because we know we can't take, there can't be a denominator of 0. So that means that there's something called a vertical asymptote at 90. So then we're going to take tan of 120, which is negative root 3. Tan of 150, which is negative root 3 over 3, tan of 180, which is 0, tan of 210, root 3 over 3, tan of 240 is square root of 3, 270, error on our calculator, so it's undivided. We know we have a vertical asymptote there at 300, negative root 3 at 330, we're negative root 3 over 3, and at 360, we're back at 0. So we're going to graph f of x on the following grid. And again, the scale this time, it's going to go pretty high. So we're just going to go up by 0.5. So 0, 1, and 2, negative 1, negative 2. Okay, so let's start with those vertical asymptotes. That's kind of our guidelines with any graph, even with the reciprocal function. So we know that that was at x equals 90 degrees. And then we also defined it 270. It's already very different because the cosine function, the sine function did not have any vertical asymptotes. So we're at 0, root 3 we have is about 1.73. So at 30 degrees, we're at 0.0, so just above 0.5. And then at 1.73, so about, right, just before 1.75, right here, halfway between. And then we're at 90, we're undefined. At 120, we're at negative root 3, which is negative 1.73. And then at negative root 3 over 3, which is negative 0.58. It should be just under negative 0.5. At 180, we're at 0, 0.58, 1.7. Okay, and then undefined again. Then we're back down at negative 1.78. 0.58, and then back at 0. So it would look like such. So very different. This is f at x is equal to tan of x. Okay, so here are the key points. Again, using the same degrees. So at 0, we're at 0. At 90, we're undefined. 0, undefined, 0. So remember, where they're undefined, we have a vertical asymptote, vertical asymptote. Okay, so we're going to complete the following information of its characteristics, again, where x is greater than or equal to 0, but less than or equal to 360. So the period, if you notice, when does one full cycle occur? It happens between 90 and 270. So taking the difference between 270 and 90, that would be a period of 180 degrees. Amplitude, again, remember amplitude from the maximum to that halfway mark. Unfortunately, they don't have an amplitude for tan. There's never a maximum. It never reaches it. It just keeps going and going to infinity. So x-intercept. So what does it cross the x-axis? Well, it looks like at 0 degrees, at 180 degrees, and then at 360 degrees. And the domain, okay, so it looks like x can be any value except at those points where they have a vertical asymptote, where that exists. So we're going to say x is an element of real. However, x cannot equal to 90 degrees and 270 degrees, because at those two values of x, the function is undefined. Maximum value, there is none. Minimum value, there is none. The range, however, there are no restrictions. Y is just going to keep going on and on and on. Okay, so notice from the graph of f at x, we see values it will never touch. These values represent the values of x where cos of x is equal to 0. We represent these values with a broken line to denote the vertical asymptotes. As well, we can see that each vertical asymptote is a multiple of 180 degrees. This is where the periodicity of the tangent function occurs.